Video calling brings people together despite their geographic distance. As our product scales for more people around the world, packet loss emerges as a major challenge, which not only causes video freeze, but more importantly, it undermines user experience. In the context of RTC, packet loss recovery should not only occur in the real time, but also occupies as little traffic as possible. So in this talk, we'll take a deep dive into our secret sauce to deliver low latency, low freeze RTC video experience. We will first describe an industry baseline, which is available in open source. Then we will take a step further, describe our unique solutions using the most recent codecs and error correction technologies, which are long-term reference and Ray-Solomon code for error correction. First, let's talk about the baselines. In the open source community, there are three mature solutions: retransmission, keyframe, and XOR-based FEC. They can be grouped into two categories: reactive or proactive. Retransmission and keyframes, they are reactive. For example, if receiver set detects a sequence number gap, it will send the RTCP NAC request to the sender set, so that sender can resend those lost packets so that receiver can resume the video playout. As you can see, because sender only needs to retransmit those lost packets, it takes as little overhead as possible. So retransmission is low overhead, but the whole process takes a whole round trip time, which has high latency. But there's another case. Under bursty loss, number of lost packets could be huge. Also, the retransmission itself could be lost as well. So that could accumulate the length of the NAC list. In that scenario, if we insist retransmitting everything with retransmission, the network actually will be overloaded. In that case, usually what we do is for sender set to send a keyframe to refresh the whole video decoding chain. However, there's a catch for the keyframe. Keyframe is large, but that may be fine because we have pacer, but more importantly, keyframe has low quality. The image is flaky. Okay, so we are done with the reactive mechanism. Let's move on to the proactive one. There's actually only one proactive mechanism to recover the lost packet, which is forward error correction, or we can just call it FEC. So as an open source solution, XOR-based FEC is available in WebRTC in form of Flex or ULP. They work similar, but the high-level idea is that the sender proactively sends those redundant information, right? And so that on the receiver side, whenever a packet loss event occurs, the recovery can happen in real time. But as you can see, it takes a lot of traffic. So in production, it's not very rare for us to take half of the overall traffic for FEC, which could have been allocated for much better video quality. So before we dive into the details of LTR and RS code, let's have a high-level overview of how they step in our whole NR mechanism to improve the whole system. First, keyframe. Just as a recap, keyframe is huge, and it has poor quality. So LTR can not only reduce the overhead, but also presents much better image quality. On the other hand, because open source community only has XOR-based FEC as its solution. As a result, RS code is really needed because RS code can actually take less overhead but achieve much better recovery property. We will come back to that later. Next, I'll hand it over to my colleague Fan to talk about LTR.
Hi, hello. My name is Fan, and I'm going to talk about a long-term reference frame, or LTR. So I'm going to first talk about what is LTR. So as we know, videos consist two types of frames. One is keyframe, which has large size and is self-decodable. Another type is p-frame, which has much less size, but usually require reference frame in order for it to be decoded. So as a result, we can see the chain dependency of the video frames. So now assuming there's some packet loss in the frame 5, which is a type of p-frame. And as a result, due to the chain dependency, the receiver not only cannot decode frame 5, but also it cannot decode all the frames after frame 5. And that's going to cause video freeze. So in this case, the receiver either has to request the sender to transmit all the missing packets, or it has to ask the sender to send another keyframe. And as we know, that both solutions are not very ideal. So here's another idea. Sender can periodically mark in some frames as long-term reference frame, or LTR. In this case, the frame 3 is marked as LTR. So after the receiver got frame 3, it can save its frame 3 in its decoder buffer. And once there's a video freeze, the receiver can ask the sender for encoding another P frame using the frame 3 as a reference. And as we know, since the receiver has already got frame 3 and saved its decoder buffer, then after got frame 7 into case, it can decode it without any issue. So we call frame 7 LTRP because the type of P frame which uses a long-term reference frame. And after receiver got frame 7, it can decode frame 7 and all the following up frames, and hence solve the video freeze issues. So that is LTR. But why do we want it? As Fengdeng also talked about before, so compared with keyframe, it has advantage of having less size and higher quality, because after all, it's kind of P frame. And compared with ENAC, it can be more efficient, especially in high-loss network. Because instead of requesting sender to transmit up to 20 packets, now receiver only need to request an LTRP. That's why we believe LTR has the potential to become a foundation block for better loss recovery approach. Because instead of requesting ENAC or keyframe, now we can request an LTRP. Now let's look at the overall flow of the LTR. It's pretty straightforward. On the sender side, most of the work is done in encoder. So encoder just need to periodically generate some LTR. And after each LTR is generated, it will be assigned a unique ID. After receiver got the LTR, it needs to send acknowledgement to tell sender which LTR it has received. We choose to use RTC head extension for acknowledgement, which means that each acknowledgement will be sent out in the outgoing video packets. And when the video freeze happens, the receiver can send RTC message to the sender, ask the sender to generate an LTRP. And the sender will start encoding a P frame using the latest long-term reference frame the receiver has acknowledged. So after the receiver got this LTRP, it can continue decoding. So while the overall flow looks very straightforward, it turns out we actually have to make sure every detail is correct to make sure the whole flow works flawlessly. Otherwise, it is very easy to see video corruption and video freeze. Here I provide you an example where we see the frame 195 is a LTRP because it refers to the 191 instead of 194. But instead of decoding it correctly, we can see this frame is actually corrupted. And that's usually caused by referring to the wrong reference frame. So it turns out to solve the challenge, we have to make sure to take up two things. First is that we have to uniquely identify each LTR frame. So that's particularly challenging because we have both software and hardware encoder. And those two encoders generate different type of LTR tokens. So to deal with this issue, we actually designed a unified API that translates them into a counter with slice head pattern. This counter is large enough, so it will not wrap around easily. And also, from receiver's perspective, it will only see one type of the long-term reference frame IDs generated by both software and hardware encoder. And the second challenge is that we have to be careful with the reference frame management. Because previously, we act every LTR once we receive every packet for the LTR. But we found that later, this LTR might not be decoded. It will be dropped before being decoded. So as a result, the receiver will not save this LTR in its buffer. So in future, once the receiver got an LTRP encoded using this LTR as a reference, the receiver is unable to decode it, hence cause a long freeze. That's why we have to make sure to check the reference frame and make sure it exists before the frame to encoder, before sending the frame to decoder. We did some performance analysis on the LTR compared with keyframe. And here, this figure demonstrates the advantage of the LTRP compared with the keyframe in terms of video quality. So the y-axis here shows you the PSNR, which is the indication of the video quality. As we can see, that LTRP achieves higher PSNR compared with keyframe. And also, it achieves high quality while maintaining much less size. As you can see, that LTRP compared to keyframe at low bandwidth conditions, its size is almost 8 times less than the keyframe. So we implement the LTR and launch LTR on Messenger, and we replace the keyframe with the LTRP under two scenarios. The first scenario is high loss conditions, which means that the receiver needs to request retransmission of up to 10 missing packets. Second scenario is that frame buffer timeout, which means that the receiver cannot decode any frame for longer than 1 second. Previously, we just request keyframe in the case, but after replacing those keyframe requests with LTIP, as expected, we see significant reduction in the number of keyframes. For example, we see the keyframe numbers drop by 37% in high-loss conditions. And also, we want to mention this reduction is done without any trade-off in the read freeze. In fact, we can even observe almost a 0.76 reduction in the read freeze, which is caused by less congestion due to the less size of LTIP. Okay, that's the end of my part. Now I'm going to transition to Fengdeng.
Let's talk about how our XOR-based FEC works in the production. FEC is not free. As a matter of fact, it's quite expensive. It takes bandwidth from the regular video traffic, which could have been allocated for better video quality. In production, generally, FEC takes more traffic as RTT, PLR, and overall bitrate grows. So the production pattern is actually very flexible. FEC could protect the packets within the same frame or across different frames. But there's a trade-off. As you protect across different frames, the recovery rate will increase. However, there will come with a natural delay because the FEC packets needs to wait for more frames arrival before being able to decode any lost packet. There's another important area is that the performance of XOR-based FEC degenerates fastly as the size of the encoding group grows. This is exactly where RS code steps in. WebRTC has a matured implementation for XOR-based FEC, such as Flex FEC and URP FEC. They work similarly. For example, if we want to protect 4 source packets with 3 parity packets, after looking up the table, here's the protection schema. Recovery is only possible if only one packet is lost in the protection group. For example, in this protection schema, parity packet 2 is protecting S1, S3, and S4. If both S1 and S3 are lost, S4 cannot be recovered at all. So let's take a step further to see where XOR-based FEC really falls short. With the same schema, on the receiver side, we have S4 where S1 to 3 are lost. In the meanwhile, we also have 3 parity packets. Because all of the packets from S1 to S3 are lost, there's no way to recover any of the information even though we have 3 parity packets. Alternatively, if those parity packets were generated by RS code, every lost packet could be recovered. In fact, regardless the number of source packets, if we generate K packets by resettlement code, it will allow us to recover up to K lost packets in any manner of combination. Here's an overview of how resettlement code FEC works. On the sender side, we have all those source packets, and depending on some mechanism, we decide how many parity packets to generate. So we feed all those source packets into the generator matrix, and the generator matrix can give us as many as parity packets we want. Afterwards, we send everything over the network. On the receiver side, if there's some packet loss for the source group, no problem. We just need to figure out how many source packets are lost and see if there are enough parity packets to recover the lost packets. Just to recap, if there are X lost packets in source packet, as long as the number of parity packets is not less than X, we can have 100% recovery. So after we arranging the source packet and parity packets in the correct order, we fed them into the decoding matrix. And afterwards, we have a working video flow. As for now, resettlement code FEC is available in every messenger RTC calls. And in this year, we are expanding the coverage to Instagram video calls. You may wonder, how can you integrate the RS code technology into your own video FEC stack? And here's our tips. First of all, WebRTC provides a very good implementation of XOR-based FEC, whose pipeline can be referenced in integrating your own RS code solution. Furthermore, codecs is the key. There are tons of different implementations for RS code, and among them, there are different trade-offs within each implementation. So you need to decide the right config so that you make the right CPU and memory trade-offs in your own application. Furthermore, in low bandwidth condition, the size of FEC packet per overhead matters, because read-only code needs some extra information for receiver to take so that it can recover the lost packet. However, those extra information are not free. You need to convey them in the header. If the header takes too much bandwidth, it will actually regress the network condition in an undesired way. As a result, you need to design a scalable format so that it not only has small overhead, but also works with other technologies like temporal layer. Last but not least, maybe it's a surprise, but RS code is not always better. In some scenario, especially when the bandwidth is not super high, XOR-based FEC can do partial recovery, whereas RS code cannot. So you need to come from your own use case and design a combination of smart algorithms to maximize the benefit of RS code. Next, I will hand it over to Fan for our final summary and future plans.
Okay, now I'm going to talk about conclusion and our future work. As we reflect our journey to enhance video stream quality in loss environments, we are really encouraged by the effectiveness of the strategies we have implemented. First, let's talk about LTR. We have to mention that LTR is not a silver bullet. At some conditions, its coding efficiency is sometimes the same equal with a keyframes, especially when the distance between LTR and LTRP is large enough, which means we have carefully designed strategies to the frequency to send LTR and also the frequency to request LTRP to make sure we do not really negatively affect the user experiences at some conditions. But we can see that with careful design of the reference frame management mechanism, LTR can achieve the same efficiency in reducing the read freeze compared with the keyframe. And that's really encouraging because that LTR achieves this same efficiency with less size and even higher quality. And now looking at Xcode, in fact, launching Xcode can already reduce the read freeze for up to 2 to 3% for Messenger. It means that Xcode does effectively recover some bursty losses that cannot be covered by XOR FEC before. And we have to mention that we just launched Xcode broadly, but we can actually explore some of the special optimization for the HD video, in which case we expect that Xcode can achieve even higher video freeze gain compared with the baseline of XOR FEC. Looking into the future, there are a lot of exciting work ahead of us. For example, we definitely want to expand the LTR coverage. Currently, we only implement LTR in Messenger when the software encoder is used. In the future, we want to actually expand the coverage to other codecs as well, such as AV1 and iOS hardware encoder. That's going to broaden our impact across various platforms at Meta. Second, we want to design intelligent loss recovery mechanism. Now we have different weapons to combat video freeze in lossy network. We have FEC, we have LTR, keyframe, and retransmission. Now challenging is that how to smartly choose which one to use under different network scenarios so that we can maximize their capability in reduce video freeze. That's going to be interesting and challenging problem we want to tackle next. And finally, Meta is committing to contribute to the web community. For example, we're actively working on contribute our group FEC implementation to the upstream WebIC. And after that's done, other players in the industry can leverage our solutions to reduce freeze and help them scale better in the group core scenarios. Okay, thank you for attending our talk. Please let us know if you have any questions.